Yes. Okay, so first, let me remind you why underlying events are important. So, in proton-proton collisions, the perturbative QCD describes and computes the partonic hard scattering, one parton from each proton. But then it fails. It is enabled to describe hadronization and underlying events. So, what is underlying event? Underlying event is arising from all what is not directly from the hard scatter, which means it can be initial and final state radiation, color reconnection between spectator partons and final state partons from the hard scatter. It can be a multiple parton interaction, which I will call MPI in the rest of the talk, or beam remanent, which are important if we want to describe diffraction and elastic scattering. So understanding what's going on around the hard scatter is important for correct modeling of proton-proton collisions and also in general after extrapolation to hadron-hadron collisions, which is especially important for the audience of this conference. Okay, so why strange particles? Strange particles should be regarded here just as another probe to study the underlying events. So there is an important theoretical reason is that the mass of this strange quark is comparable to the QCD scale. So calculations from perturbative QCD are not possible. So we need measurements to tune the model. And then you have, I will talk about K0 short and lambda, which are just the lightest strange meson and strange baryons. So they are easier to produce. They are not only easier to produce, but they are also easier to tag by identifying their displaced decay vertex into two charged particles, pi plus pi minus for K0 short, pion proton for lambdas. So in our jargon, we call this secondary vertex V0, and it's typically after a flight of about 3 centimeters and about 8 centimeters for K0S and lambda. Okay, so this is the title of today, and I remind you just that CMS published this result 9 years or 11 years ago, but at 70 eV. Sorry, I am not used to this. Okay, so where is the underlying event? Since I told you that there is a hard scatter first. So even a very simple minimum bias is biased because there are particles which have a PT larger than the average, which have fired the trigger. We need to define in our events the topology where to look to be sensitive to underlying events. So here in this cartoon, I describe a method which has been pioneered by the CDF collaborations more than 2 decades ago now at the Tevatron. So basically, we look for the leading jet in this event, and we look at and we say all the region around the leading jet is the hard scatter, and also the back-to-back is hard scatter, of course, to conserve momentum. And then the other regions, which are these regions, we call them the transverse region because they are transverse. The underlying event is hiding here. So we have the towards and away for the scatter, the hard scatter, and the transverse region for the underlying event. So what do we need to perform now to make the study? As I told you, we need to acquire events representatives of hadronic interactions. So this means the least biased hadronic interaction, the least biased collisions. So we use a minimum bias trigger. We need to get rid of pileup. You know that at the LHC at nominal collisions in each bench crossing, we have in run 2 up to 50, 60 individual proton-proton collisions. So if you do not get rid of this pileup, you will mix up underlying events from different collisions. So we need to operate LHC at very low luminosity. This is a key point for such analysis. And then we need to identify the strange particles by their decay vertices and invariant masses, which means precise tracking and vertexing and good momentum resolution for the invariant masses. I did not want to go into numbers here because, okay, it's not the subject of the talk. We need to reconstruct relatively low PT jets and reconstruct charged particles with a large efficiency. This means we need a large tracking volume. And of course, the Atlas experiment fulfills all these requirements. So this is an image of the Atlas detector. It has just, I will not describe everything here. We have the tracker here inside. We have the calorimeters here, and we have the muon system all around. And this analysis uses informations only from the tracker. Okay, so this is the tracker. So we have first two silicon detectors. So here we have first the pixel detector surrounded by a microstrip detector, and all around we have the gaseous detector. So we need also to trigger. So we are using also scintillators, which we call MBTS. So basically, these are 12 sector per side at plus Z and minus Z, Z being the beam direction. And yeah, you can see the how the sectors are made on each side, and they are located at plus minus 3.5 meters on both sides. Okay, now let's go to the data. So we have used 6 LHC fields recorded by Atlas 9 years ago. So as I told you, to get rid of the pileup, we had only 29 colliding benches. Typically, in the typical LHC run, we have 100 times more. And we had a larger betatronic function and smaller benches to reduce further the luminosity. So we ended with a mean number of inelastic collision per bunch crossing between 3 per mil and 3% instead of an average of 50 during the run two. So 5 of these 6 fields were taken with this trigger. We require at least one MBTS sector, I just showed you, above threshold. And the 6th field for other analysis, we have required at least one MBTS sector above threshold on both sides. So we ended up with 110 million and 20 million minimum bias recorded with each trigger respectively. Now I will say a word on simulation, which is the important, which is a very important ingredient of this analysis and of the future of those results. So we have used 3 Monte Carlo samples. The first one, I guess it is well known in this community, is IPOS with the LHC tune. So it has Gribov-Ricci. It is based on Gribov-Ricci theory. The MPI are included, and also nuclear effects. For Pythia, this is the historical preferred generator for particle physics. It uses, as we saw yesterday, just a T-channel gluon for the hard scattering and Pomeron exchange for diffractions. The MPI is included with the impact parameter approach, and we have used 2 tunes here, A2 and Monash. The Monash tune is not pure Monash tune. It has also an alternative color reconnection model. Okay, now let's go into the data. First, if we want to identify jets and to identify K0s, etc., we have first to reconstruct prompt tracks. So we have used, you can see it here, we have used an original selection for those charged tracks, which we call low PT track, you can see here that the low PT of these tracks are down to 100 MeV. And then we applied additional quality cuts on on minimum PT, on acceptance, on impact parameters with respect to the primitive, the primary vertex, the point of collisions, and then a few minimal hits requirements and chi-square requirements. Okay, when we are happy with this selection, we go and reconstruct jets. So we use only prompt tracks as input. This means that we do not use, as I told you, calorimetric and they are reconstructed using the anti-KT algorithm with this radius in units of pseudo-rapidity and azimuth. And then we ask the leading jet, the highest PT jet, to be within 2.1 because we are using 2.5 here for the tracks, but we have to take into account, of course, the radius of the jets. Now, the K0 short and lambda identification. So we cannot reconstruct them by using only the prompt tracks because these particles fly, and this is why we can reconstruct them. So we need to allow what we call in our jargon large radius tracks starting at larger radius. Okay, so we have tuned also our reconstruction to be able to do this, and of course, such tracks use only unused space points by the previous sets of tracks, the prompts one, and of course, the impact parameters are loosened, requirements are loosened. If not, yeah, I mean, if you want to reconstruct something which has flight, you have to do this. Okay, and then the V0 finder algorithm is very simple. We just iterate over all possible pairs of oppositely charged tracks using both sets, the prompt I just explained and the large radius tracks which we have here. And then for each V0, we fit it with one of the three hypotheses, the K0 hypothesis, the lambda and the lambda bar. And then we apply selection. The most trivial one is just to ask that the invariant mass of the V0 is in agreement with the mass of K0 and mass of lambda, and few other quality cuts which I won't describe unless you have question. Okay, so now we have tracks, we have jets, we have strange V0s. Now let's go to the event selection. So the event selection is really very simple. Both in data and Monte Carlo, we ask to have one and only one primary vertex. And then when we have these events, we ask them to have at least one track higher with a PT higher than 1 GeV. This is to get rid of the background coming from beam gas, beam halo, and even cosmics. And then once we did all that, we have to correct for the detector effects. Atlas is a very good detector, as we all know, but it's not idealistic. So there are resolutions, efficiencies, etc. So the events are corrected for trigger efficiency. The tracks are corrected for their reconstruction efficiency. The V0s are corrected not only for efficiency, but for fakes, because sometimes we have V0s and we think that they are V0s, but in fact they are not. And then there is also the migrations in PT bins of the reconstructed jets, which we have corrected by a procedure called enfolding, where we use Monte Carlo. We have used the ISVHECRI simulation. And to illustrate all these corrections, I show you just one example. Here you have the efficiency or the fake fraction of V0s as a function of the decay length. It's not the decay length, it's the projection of the decay length on the transverse plane, means on the plane parallel to the beams. This is why it is called R, like a radius. So basically, if you want, it's the decay radius. And here, in these three bottom curves, you can see the efficiency. It's around while 45% and 30% for lambdas and for K0 short. Here you have the fake fraction. Well, it's 1 minus fake fraction. This is just a trick to be able to put them on the same figure. And the jump that you can see here are due are where the layers of our detectors are located, because of course if you approach a given layer, then the probability to have parasitic V zeros coming from hadronic interactions with the material are important. The probability is important, so we had some very strong cut there. Okay, now the systematic uncertainties. I told you about selection, corrections, whatever. Each time you do this, of course, you introduce an uncertainty. These are the list of the uncertainties we have taken, which have been taken into account. So the enfolding prior is just, is it working or not? This enfolding procedure on the PT, just I told you. The enfolding model, I told you that we used EPOS LHC, but this is just an arbitrary choice. So we have estimated the same error. We have estimated this error by using another Monte Carlo PTI A2. We have in general strange hadron uncertainties, which are the differences in fake estimation between data and Monte Carlo. Material budget, as I just told you, the material estimation is very important. And the statistical error from Monte Carlos. We have the prompt track uncertainty coming from the material budget and the selection, and a non-closure correction. Okay, I will not go much into detail here. The important message is on the next slide. Here, first, please look just the to the different colors here, which are the different systematics I just presented for you. This is for lambdas and this is for K zeros. The data is normalized to 1, so that you can see that the most of the systematics while the total systematics, which is the gray band, are well below 10% in both cases. So this is the first message of this slide. The second message concerns the observables I will use now to show you results. Here you see that the number of K0S is by unit of pseudo rapidity and azimuth. So basically, if you multiply by the total acceptance, you get the number of K0 per event. So I will call this multiplicity normalized per event. Here, it is normalized by the child that tracks in the event. It gives you kind of a percentage if you want. This is not completely true because lambdas and K0s are neutral, but anyway, it gives you, well, the fraction of strangeness in each event. Okay, I think that the next slide is results. Yes, this is for results. I still have time, I hope. Okay, thank you. Okay, so first start with the K0S. So here you have the K0S normalized by event as a function of leading jet PT for the three regions, the away region, the towards region, and the transverse region. And yeah, we can say a lot of things here, which I try to summarize in those few lines. When you look to data, it appeared clearly that we have a soft regime at low PT here and a hard regime for PT higher than, let's say, 10 GeV. Okay, so this is what the data tell us. If you look to EPOS is really very close. It does a very good job in the soft regime, but in the hard regime, it shows a dip here everywhere in all three regions, which is absent from data. So there is a clear problem there. For for the others, I mean, we can just say that the PTA A2 model describe well the shape, but it underestimates the multiplicity of K0s. Monash is good in the towards region, which is here. So Monash is the red. You see that Monash really follows the data. So this is the same, but this time the K0 multiplicity is normalized by the charged particles in three regions, away, towards, and transverse. Here you can see that the soft to hard transition in data is really thank you, less evident. And more or less the same observations here. EPOS is not as good here, and the Monash is good, although is good in the towards region. Now the same thing, but for lambdas. Uh, so for EPOS, you see that the same applies. It's very good in the hard in the soft regime, but it has this dip once again, which is not in the data in the hard regime. And yeah, for the rest, we have always Pythia, which is good in the no, sorry, this time Pythia is good in the away and transverse region. So it's something that we, of course, we did not understand, and well, these are just our sorry data. And finally, these are the results for lambda by charged by normalized for charged particles. Okay, so we can see that that EPOS is close to data in both regimes. Pythia Monash is better in the towards region, but it is in general Pythia Monash is close to data this time except in the towards region. And a general remark of all the four slides I have shown are just that except Pythia Monash in towards, all models underestimate the strangeness. Okay, the interpretation, maybe I will skip it. If there are questions, I will be happy to discuss this with you because I have only 2 minutes left. Now let's concentrate I still have two slides. Let's concentrate on the hard regime where most of the multiplicity goes to a constant which saturates. And then we look to the multiplicity of k-zeros and lambdas as a function of the charged particle in the transverse region. So this works, this uncharged transverse, this works as a proxy of the number of MPI. And you see that in both particles go to a constant here, which means that they are scaling linearly with the number of MPI. Okay, so these are another and the last results I will show you today. So it's we are always in the hard regime, and this time this is the ratio of lambda bars on K0s. Maybe this is the ratio of its proxy to the ratio of baryons on mesons as a function of number of MPI. And you can see that it will scale, in data at least, it will scale linearly. I let you look to your favorite Monte Carlo. And here is the same ratio. Yes, but in another region. So this is the towards region, and this is the transverse region, and they both follow this constant, which means that they are scaling linearly with the number of MPI. The conclusions. So I have shown you the properties of underlying events with the strange hadrons at 13 TeV with Atlas. They were identified by the decay, by the secondary vertices decay. The strange hadron multiplicities were compared to different Monte Carlo. So PTA A2 underestimates systematically the strange hadron yields by 40 to 50%. PTA Monash is much closer to data. EPOS is the best at soft regime and underestimate the yields at high PT. So in general, EPOS is in best agreement for yield variation with the number of prompt charge particles in the transverse region. Means maybe it's the better candidate to be able one day maybe to describe completely the underlying events. So this data must be used to improve the modeling, of course, and more results are coming from Atlas. So stay tuned. Thank you.
Thank you very much. We have time for some question. Tanguy and then Chloe.
Thank you, very nice. So can you go back to the interpretation slide that you
Yes.
were a bit fast?
Thank you. Yeah, I didn't. I was not fast. I was.
Yes.
I did not show it.
Yeah. So then I can comment.
Yes.
So in fact, so for EPOS, it's really true predictions, not only because even when it was tuned, even this kind of analysis were not existing. So it's really nice. It was already done at 7TV, and it was, and at this time I checked why it was working well. And then the thing is that when you probe around up to 5-6 GeV where it works well, is the leading particle is actually coming from the core part, this core corona thing. So you have the flow.
I didn't get it from.
In EPOS, one of the what's different from PTI is this core corona process where you separate
yes.
and you have a flow on some part of the particle.
Okay.
So the leading particles there come from the core because it has flows, especially with lambdas and things like that. So this part is actually really well described then by the core corona process. And then when you go to higher PT, indeed we have a deficit of jets and high PT particles in EPOS LHC. So that one of the goals of EPOS 4, for instance, is to correct for that, and it's done now, so it should be better. So that's very interesting. So the interpretation of the data is very different if you know that in fact this is really due to this core corona. If I switch it off, then it's gone. It's really the leading particle comes from the plasma kind of thing with flow, and that's why it works better than for PTR. It's not jets, in fact. It's really
so you are saying that what I wrote here, the first one, does not apply to EPOS because
not really. I mean, it's a mix because of course we also have MPI and so on. So it may play a role, but what is really important here, especially for strangeness, because the core enhances strangeness and the flow is larger for this particle. It's really that you probe particles which are not really coming from jets, but from the, let's say, the medium which could be created. Yeah.
And do you understand from where the dip comes?
Yes, and then the dip is, so you have this part is really the core, so it works well. And then I don't have enough jets or enough MPI, I don't know. And then you go to the hard regime, and then there is a deficit. So you have a transition from this soft part, which is not due to jet, to the jet part, where it's not well done by EPOS.
I see.
Okay. But we can discuss offline, of course.
Okay, thank you.
Yeah, Chloe was.
Hi, thank you for your talk. Regarding the PTA tune, so A2 is an Atlas tune, right?
Yes.
Is there a plan, therefore, to make another Atlas tune that would match better these datasets?
I am not in contact with people who are working on it. Really, I don't know. But certainly, I mean, yes, we know that in Atlas there are people who are working on this, and they expect a new tune. But this is not the only results. We have a lot of results which are coming, and it may take a year, 2 years. I don't know. So I don't know the exact answer, but stay tuned.
Yeah, I also had a question about the K0 per event and per charge from particle. So is that the difference, which I couldn't make any sense out of that? Is that related to what Tanguy just discussed with the core corona effect? Sorry, there is a difference between K0 short per event and per charge particle. I mean, So EPOS describes per event well the
Okay.
soft part, but not the
This one.
yeah.
Yeah.
Right. But if I go to per charge particle or prompt charge particle, it looks different. So I was wondering why that is different.
Ah, with the second part.
No,
this is
actually, what you just showed. I mean, slide K0 showed per event. That one. So there the
No, this
EPOS
is lambda. This is lambda. Right.
lambda. Go to K0.
Okay, so this is K0 per
Previous.
okay, so this
Here
is
per
the
event.
yeah.
So here EPOS describes the soft part
Yes.
well,
Yes.
right? And then if I go to next slide, per prompt charge particle, there it doesn't.
Yeah.
And I was wondering about that. How come?
I don't know. I mean, we can think about really. I don't know. There are experts here from IPOS which can certainly enlighten us, but really I don't know.
Yeah, I think then we have to stop because we're already running into the next talk. Okay.
Okay, then I give the microphone to Anne.
No, it's very simple. If you come next to the slide where you have uncharged dependence later on, right? Yields of strange
No, we have for
as a
K0.
function of number of charged. If you use standard QCD, you have it flat. You don't have this rise you see in the data.
Yes.
To get this rise, you need something special. You need some kind of collective effects, be it color reconnection or like this in NIPOS, like thermodynamical description. You don't have it from QCD. You have just flat dependence. You get the rise as a function number of charge only because you put something extra. And the same here. In IPAS, you have this extra thermodynamical, the core part. It helps to get it at relatively small PDs. So the deep is not the deep. It's just enhancement of the smaller PTs because of
Yeah,
the core.
this is what just he said. Yeah.
Okay. Thanks. I think we have to finish here to get to the next talk. And I think we should continue the questions in the coffee break. The next is by Joachim Menzer. So we talk about LHCF minimum bias events and PP collisions. So let's give us a second to set up the slides, and I'll give you the usual